Hi, give me just 1 second. Sorry, I'm having some technical difficulties here. So just trying to make sure that this is gonna run pretty smoothly. So just give me a couple more minutes and then we can start.
Sure thing.
Okie doke. First of all, can everyone hear me? Awesome. Okay. Welcome. I'm gonna start recording now. Hang on. Sorry, I'm using had a series of technical difficulties in the last half an hour, and I'm using an unfamiliar computer, an unfamiliar tablet, and I lost part of my Zoom menu. So we're just gonna have to try to find it, maybe, or not. Oh, it's not even letting me write anymore. Darn it. Okay, give me 1 second. Again, I'm sorry. Oh, there we go. Okay. Okay. Maybe. All right. Welcome, everyone. Again, sorry about the delay in getting this set up and started. My name is Liv. I'm going to be your guided study group leader for the semester. And basically how these usually run down is we kind of jump in this room together, and you can ask questions. We can go through some practice problems. It's kind of like an informal session where we just try to like go over like what we kind of did this week. So that being said, I record these sessions and post them on my YouTube channel. So after this is done, I'll just post it pretty much right away, and I'll make an announcement about it. So you can access those every week if you can't make it to the live session. And yeah, you guys can talk to me via the chat, but what I found easier is if you guys are comfortable hopping on the audio, you can just talk as normally, and I should be able to hear you if I don't get too confused by this computer. Yeah, that's basically what's up. Are there any questions about like generally what we're up to in a GSG, or do we want to just jump right into the material for this week?
Material's good for me.
Alrighty. So this week we talked about sections, oh lordy, sorry, the tablet's giving me some grief, but we talked about 1.4, 1.5, and 1.6. Nope, 1.6 and 1.8 this week. So we basically did a lot of coverage of limits and tangent lines, and we're setting ourselves up so that we can do some calculus later on in the semester. Let's start with 1.4. Sorry, I've got now two computers open in front of me trying to track down the problems in one and write on the whiteboard in the other. So let's start by doing a problem from 1.4, which is the tangent lines. If I can, yeah. So this is kind of working with tangent lines. Is there a problem that you kind of want to do, or I'll just, find one that kind of makes sense in a second if I can find the page. I'm so sorry. Usually I'm much more on top of this stuff, but like I said, it's been a wacky half an hour. Okie doke. Let's just start perhaps with let's try problem 5 to start with in oh no. Okay, so this is fine. This tablet is fine. Let's start with problem 5 in section 1.4. So I'm currently on page 50 in the book. Please stop doing this. And we're going to do problem 5. So if a ball is thrown into the air with a velocity of 40 feet per second, its height in feet in t seconds later is given by the function y is equal to 40t minus 16t squared. Find the average velocity for the time period beginning at t is equal to 2, lasting a series of seconds. And so they're getting progressively larger or smaller. So where am I going to start with this problem? It's asking us to find the average velocity for this time period. So how am I going to find average velocity? What is average velocity? Thoughts, anyone? Okay. Yep, basically. So average velocity is the change in position. So we're going to use delta to signify change over the change in time. So this is a change in something as it relates to a change in something. And so our position is going to be given by y. So our position is y of t, and our time is given by t. So we're just looking for delta y over delta t. Or as you put it, y of time 1, or y of time 2, excuse me, minus y of time 1 over time 2 minus time 1. So that's how we're getting our average velocity. Is everybody cool with that being averages and how it specifically relates to velocity as position over time? Stop me if anything, anything's going wrong. So back to the problem at hand, or like number 1, we need to find the average velocity for the time period beginning at t is equal to 2. So we're going to say that like t1 is equal to 2, and then t2 is equal to what for I? It's just going to be t1 plus that period of time. So it's just lasting that period of time. So it'll be not 0.5, but 2.5. Oh, wow. So it'll be 2.5. And then we can just set it up exactly like we did over here, where the average velocity is equal to delta y over delta t, which is equal to y of 2.5 minus y of 2 over 2.5 minus 2. So y of 2.5 means we're just going to substitute in 2.5 to this equation up here. So it's 40 times 2.5 minus 16 times 2.5 squared. And then this is going to be minus 40 times 2 minus 16 times 2 squared, all over 0.5. So another way that we could see this is that this time, how long the time period lasts is the change in time, if that makes sense. So for any of these 1 through 4, what we have here on the bottom as our delta t is always just going to be the number that they gave to us, because that's the length of the time period or the change in time. So we're going to be plugging this into a calculator. So if anyone wants to start plugging stuff into a calculator as well, that would probably be pretty helpful. That is not a calculator. So this is going to be, this is 100 minus negative 32 total. So there's our total for number 1. We probably don't have to go through 2 through 4 if you guys don't want to, because it's basically just doing this on repeat. What does this mean about the ball that we're throwing? Yeah, we're throwing it with a ball. So what does this mean about the ball that we're throwing?
It's on its way down.
Yes. Or rather, is it trying to relate this to stuff that we're doing later in relating position and velocity and acceleration. But yeah, let's not do that. Let's just say for now, the velocity of the ball is going down. So the change in the ball's position is negative. So it's on its downward arc.
This question was also on the WebAssign.
Mm-hmm.
And they had us do it a little bit different way. I don't know if it'd make it easier or not.
What did they have you do?
Like for the average velocity, they had, maybe it'd be easier to type it in.
What was that?
Well, for the velocity, they had us. It was a different formula. It ended up being negative 16h minus 24, and then h was the difference in time from the 2 seconds to whatever you know, the 0.5, 0.1, 0.05, 0.01.
Okay.
So instead of writing out, you know, the whole thing,
Yeah.
y times 2.5 minus y times 2 over 2.5 minus 2, it just had
Okay.
you plug the difference into h, because it used the, you know, it was y times 2 plus h minus y times 2,
Mm-hmm.
you know, y final minus y initial over 2 plus h minus 2, which would be the final time minus the initial time. And that's, you know, once you solved it all down, it just ended up being negative 16h minus 24. And then all you had to do was just plug in the, you know, the different times,
Yeah, yeah.
however long it lasted. It just seemed to make it go a little quicker.
All right, yeah. Well, if that like works for you, then like definitely. I just kind of wanted to go through including like the definition of like what the velocity is.
Right.
But for sure, for sure. Yeah, that's also a handy way of doing it. Do you guys want to keep doing problems from 1.4? Do we want to try doing some from 1.5? Because we've got like 4 different sections to cover this week. This is really the session is whatever you guys want to make it. So if you want to talk about 1.4 for however long you want to talk about 1.4, then that's cool. Okay. Okay. Let's do a quick problem from 1.5, and then we'll do 1.6 and 1.8. Okay. Oh, this Zoom is really getting to me. Keeps like removing my menus. Okay. So for 1.5, now we're getting into limits, and the important, like, I guess the important thing to recognize like about this chapter is, or this section is, like what a limit kind of looks like and how it's like probably a little bit unfamiliar to you guys to see something that looks like this. Sorry, that's an F. And it won't let me erase it with a keystroke, so I'm going to rewrite it. So it's just important to be able to read what's happening here, which I'm sure that you guys can do now that we've like gone through it for a week. But it's mostly about like legibility, I think, here. All right, so let's start off with number 3. Just explaining briefly what the meaning of each of these limits is. Let's just do 3a. So we have this. So tell me, what does this limit mean? Like, read this for me and tell me like what some significance is. Yes. So the limit from the left and the right both equal infinity. So if we have a number line, you know, with like -3 being right here, we know that from the left it's going to infinity, and from the right it's going to infinity. So what we have here is an asymptote. right? And so the value of f of x can be made essentially as large as we want it to be by taking an x value that is really close to -3 but not equal to -3. Right? Everybody cool with that? Everybody on board? It's basically just identifying like what like an asymptote kind of looks like with the limit. So sorry, my chat is not behaving correctly. Yep. All right. So let's also maybe do does everyone have their books with them? Like if there's like a graph in the book, could you see it? Awesome. Okay. So let's do number 5 as well. So there's a graph in the book for number 5. And for the function f, which is given via that graph, state the value of each quantity if it exists, and if it doesn't exist, explain why. So we have that graph from the book, and let's just start with A, where we're looking at the limit as x goes to 1 of f of x. So the limit of as x goes to 1 is equal to what, or does it not exist? It's equal to 2. And that's just because as x approaches 1, the values of f of x are approaching 2. So it's equal to 2. What about if we have the limit of f of x as x goes to 3 from the left? Does this exist? Yeah, it does, and it is equal to 3. Or is it equal to 3? It's coming in from the left. Yes, 1. So, and then if we have it coming in from the right, it's going to be equal to 4. And what about when we have the limit of x going to 3, not from the left but from the right, but just generally speaking? Doesn't exist because the limit from the left is not equal to the limit from the right. So that, I think, is the important takeaway from 1.5, is kind of recognizing what these limits look like and like beginning to like solve a couple problems with them. Okay, so 1.6, if you guys are okay with being done with 1.5, we can do some problems from 1.6 because that's what people seem to want to do. So let me flip to 1.6. Okay, assuming there's no objections, so we're going to do some problems from 1.6. I'm currently on page 70. And we're going to start with problem 3. So we're going to evaluate the limit and justify each step by indicating the appropriate limit laws. So I've got this limit, which is the limit as x goes to 3 of 5x cubed minus 3x squared plus x minus 6. All right, so let's evaluate this limit. what's the first thing I'm going to do? Which limit laws am I going to start to use? You don't have to remember the numbers, just like walk me through what I'm doing. Yeah. I think that the first thing we should do to like start applying those limit laws is breaking it up and saying that this is equal to the limit as x goes to 3 of 5x cubed minus the limit as x goes to 3 of 3x squared plus the limit of x and then minus the limit of 6. And so these are numbered in here. I don't really think that we need to know about the numbers. I don't think that particularly matters. But basically what we're saying is that we can do that and break it up into these different parts, which will come in handy breaking it up into these different parts later on. And it might be something that you're already like intuitively doing. But then I think we're going to pull out constants, I think is a good idea, because right now we have this thing that's built with a lot of constants into this. So this is like a very simple problem, but we want to make sure that we get all of like the fundamentals here. So this is going to be 5 times the limit as x goes to 3 of x cubed minus 3 times the limit as x of x squared as x goes to 3 plus the limit of x minus the limit of 6. So now I think we can substitute in 3 for x. So we have 5 times the limit as x goes to 3 of x cubed, so this is going to be times 3 cubed, minus 3 times 3 squared plus 3 minus, what is this? X is going to 3. What is going to be the limit of 6? 6. So this is going to be 5 times 27 minus 3 times 9 minus 3. So 5 times 27 is some number. 135 minus 27 minus 3. So our answer is going to be 105. And so there's our answer. So that was just kind of like basics, like let's start evaluating this limit. And so that was a pretty simple limit to start with. What about if we try something that's a little bit nastier looking? How about number 9? So for number 9, we have the limit as x goes to 2 of the square root of 2x squared plus 1 over 3x minus 2. So we're going to start breaking this down. Using limit laws. So walk me through breaking this down. What's the first thing I'm going to start to do to break this down into something a little bit more manageable? Like, what can I do to manipulate this? Well, I'm going to start, I think, maybe by getting the limit underneath that root. So this is going to be equal to the limit of this fraction. Right? So this is, again, the limit as x goes to 2. So we're allowed to do that. And then I'm going to divvy it up even further. I'm going to say this is the square root of the limit as x goes to 2 of 2x squared plus 1. And then the limit as x goes to 2 of 3x minus 2. And then I can do basically the exact same thing that we did last time, which is split it up even further. So I'm going to have 2 times the limit as x goes to 2 of x squared. And then I know that the limit of 1 is going to be 1, so I'm just going to, I'll write it out, actually. I'll write it out so that we don't lose track. And then we still under the square root. And then we have 3 times the limit of x. And this is the limit of 2. So then I can continue to evaluate this. We're going to have this square root 2, and the limit as x goes to 2 of x squared is going to be 4 plus 1 over 3 times 2 plus 2, and we are going to finish with the square root of 8 plus 1 minus 2, yes, minus 2. That's a minus sign. So that's 8 plus 1 over 6 minus 2, so this is 9 over 4, so this is equal to 3 over 2. And that's my answer. So the reason that we're doing this so painstakingly is to get familiar with what we can and can't do with limits, and where we can, take them under the root sign. Like, can we do that? Yes, we can. Just getting ourselves more familiar with being able to take limits and work with them in a productive way. Does anyone have any questions about what we just did? And do you want to try to do a little bit more wonky ones, maybe, just like generally like evaluating the limits without all of these laws? I think we'll just do that. So let's try to do, let me find a good one. How about you guys walk me through taking the limit of number 25. So here we have the limit as t goes to 0 of root 1 plus t minus root 1 minus t over t. So, what's the first thing that you're going to want to try to do? Plug 0 in for t. Can we do that? Okay. If we plug 0 in for t, what's going to happen? We're going to get a big old problem where we're going to have root 1 minus root 1 over 0. And we can't do that. So we're going to have to find some way to turn this into something that's workable. Do you have any suggestions to turn this into something that's more workable? You said separate. What do you mean by that? Any ideas? This is far from the most intuitive thing that has ever been done. But we're going to multiply it by 1, okay? But our 1 is going to look a little weird. It's going to be something over something, and it's going to make it so, yes, exactly. So we're going to multiply it by root 1 plus t, plus root 1 minus t. And then, again, because we're doing it by 1. So this is going to turn it into the limit as t approaches 0 of root 1 plus t squared minus root 1 minus t squared over t times root 1 plus t plus root 1 minus t. So now I've got this monster that we get to deal with. But it's going to be more workable to do this than the original one, which we didn't know how to do. So let's break this down a little bit more. We're going to end up with the limit as t goes to 0 of 1 plus t minus 1 minus t over this denominator. So this is going to turn into 2t over t times 1 plus t plus, plus root 1 minus t. And these t's are going to be able to cancel. So that's going to get us into something that we can actually like find a limit with, right? So now we have the limit as t goes to 0 of 2 over root 1 plus t plus root 1 minus t. So as t goes to 0, now we can just substitute in 0 for these t's, and we're going to end up with 2 over root 1 plus root 1. So this is going to be 2 over 2, and our answer is going to be 1. Any questions about that? I always forget about multiplying it by the conjugate. Honestly, that's never something that I think about. So I see a problem like this and I'm a little nervous about how to do it, but that's basically, I think, what's up there. Do you want to try another limit problem? I know people tend to struggle with anything with roots in it, so I've kind of been thinking about just picking out some of these root problems, like maybe number 29. So here we have the limit as t goes to 0 of 1 over t root 1 plus t minus 1 over t. So again, our first instinct is just to try to sub in for 0, which is not going to be productive in this case because we've got so many t's on the denominators. What do you think I should do instead? What's the first thing I should do to start making this something that I can work with? What do you mean by separate?
Take the limit of the first fraction minus the limit of the second fraction.
All right, let's do it. So now what am I going to end up doing? I've separated them out. Can I work with this? Do I know how to turn this into something that I can find the limit of? Because this limit does exist for this whole problem. And it's not infinity. So a lot of this, I think, at least for me, when I was learning this for the first time, a lot of this was just trial and error. Like, can I do this? And a lot of the times, if you attempt to do something, and you keep chugging along at it, you find out that there's like a little bit of an issue here. In that, if I substitute 0 in for t here and 0 in for t here, I'm going to end up with 1 over 0 minus 1 over 0. And that's a problem in that I don't know how to do those limits yet. So yes, common denominator is what I would do. Okay, erase all of this. Sorry, my eraser is really weird on this computer. So let's do a common denominator. And our common denominator means that we're going to be multiplying this by 1 plus t and this by 1 plus t. So I'm going to end up with 1 minus root 1 plus t over t root 1 plus t. Right? Yep. Okay. So now, what do you think I should do? I'm going to do the exact same thing I just did. I'm going to use a conjugate to try to make this into something that I can work with. So I'm going to multiply it by 1 plus root 1 plus t over 1 plus root 1 plus t. And this is going to turn into, sorry, when I do this with the little arrow thing, that's my kind of way of saying the limit is implied. I don't want to write down the limit as t goes to 0 every single time, because that's just a waste of time and space. So the limit is implied throughout this whole thing. We're going to remember that it's there. So this is going to turn into, these two multiplied by one another, and that's going to be 1 squared minus root 1 plus t squared over t root 1 plus t times 1 plus root 1 plus t. So we're going to turn this into, just going to loop all the way around. This is going to be 1 minus 1 minus t. So that is going to be negative t over, oh, we don't need to distribute that. I was about to distribute that, but we don't need to. Because this is, so this t is going to cancel, and this is going to turn into negative 1 over root 1 plus t times 1 plus root 1 plus t. So now we can sub in the 0, and we're going to end up with negative 1 over 1 times 1 plus 1. So this is going to be negative 1 over 2. And that's how we break that down. Any questions about what just kind of happened with these two problems, finding these limits, et cetera, et cetera? Because if there's not, we can move on to 1.8, which is continuity stuff. No questions, comments, or concerns? Oh, yeah, let's do it. Okay. So we've got this function that looks like this. And the limit is going to 0, presumably? Okay. So walk me through how you approached this to start with. Like what was your first kind of step? Like what did you start to do here? Plug in 0. Okay. Didn't quite work out because we've got that 0 in the denominator. What was your next step? Yeah. Okay. So how did that look? Difference of the cube law. Yeah, I would start with something like that. Sorry, I'm looking at this. I'm trying to like remember. So yeah, we've got to turn this into something that's workable, basically. And the difference of the cubes is when you have a cube minus a cube, you can turn it into something times a quadratic, right? Sorry, a lot of this is just like using the algebra that you have, and sometimes my algebra is a little rusty. So cube law looks like this is going to be, it is h plus 3 times, no, it's not times, it is h plus 3 minus, where did my eraser go? Okay, it's h plus 3 minus, oh, that's red now, that's not what I wanted, minus 125 times, oh, there we go, thank you, times h plus 3 squared plus h plus 3 times 125 plus 125 squared. So this is going to turn into h minus 122 times h plus 3 squared, which we should probably run out, right? Do you think we should do that? I think we should. We'll see if I regret it. B is 5. Thank you. Ugh, I'm a fool. Okay. That is going to make things a lot nicer. Not 125. Duh. Minus 5. Because it's cubed. So this is h minus 2 times h squared plus, what is that, 6h plus 9 plus 5h plus 15. This times 5. And then this is plus 5 squared plus 25. There's a lot nicer numbers to work with. Is this, like, stop me if you see me making any like basic algebra mistakes, because trust me, it happens and it can really make it tough to solve. So h squared plus 11h plus 25 plus 15 plus an additional 9. So that's 49. So this is this going to get us out of our 0 in the denominator, though, is my question. Is this going to help us with that? Or is it going to get us? Okay, let's. Do you know, yeah, do you know what the answer is supposed to be? You had the example, it's supposed to be 75. I don't believe that. Where'd you get this? WebAssign? H plus 5, not H plus 3. I don't see how that would change much. Unless, oh, it might change the cube shenanigans. Okay. Yeah, it would change the cube shenanigans. So I think what's going to happen here, I think I'm going to follow what's going to happen here. Let's redo our cube shenanigans with the 5. Let me get this erased. No, you're good. I mean, I'm pretty sure that this is like a limit to infinity, the way that I have it written right here with the 3. And that's not something that you guys have really done, I think, limits to infinity yet. So I was a little confused as to where you got this from WebAssign. But last semester we did have some problems with some of the limits in WebAssign not really being like workable with the material that we were working on. So I was wondering if this was one of those examples. But with the plus 5, let's try it like this. So we have h plus 5 minus 5, because our b is 5 and not 125. And then we have h plus 5 squared minus h plus 5 times 5. Is it minus or is it plus? You wrote that down earlier. I'm just going to scroll back through the chat. And then it's, I think, plus 25, which is 5 squared. Come on, chat. Work with me here. It is plus, not minus. Okay, so redoing this cube problem. Now we have h plus 0. This is times h. So this is going to get the h out of the denominator, right? Do you kind of see how this is going to line up? We're going to have a whole bunch of junk in the numerator, but it's all times h, so we can cancel the h from the denominator and the numerator. So this is going to be h squared plus 10h plus 25 plus 5h plus 25 plus 25. Stop me if there's any issues. And then this, again, is all over h, so we're going to bring that in. And now we can cancel out those h's. And now we can sub in the h goes to 0. So we have the limit of h goes to 0 of h squared plus 15h plus 75. And so this is going to be equal to 0 plus 0 plus 75. So our answer is going to be 75. So yeah, I can see how that would be a very confusing problem if it was h plus 3. But with h plus 5, yes, it is going to be 75. So we're always just trying to manipulate this into something that we can like do some cancellations on. The reason that we couldn't do cancellations on the other one is because instead of having an h here, we had an h minus 2 or something like that. So we couldn't just cancel out this denominator h. But because we're using the 5 instead of the 3, we can cancel out the denominator h because we have the cancellation of this 5 here. So, does that make sense? Sweet. Let's wrap up with a couple of continuity problems. Unless you guys have any more questions about like limit problems that you had problems with, because like it's just like kind of got to work through it. Like it's a new problem every time, and we can definitely talk through any ones you had issues with. So let's maybe try. Let's see. Let's try maybe number 11 in 1.8. So I'm currently on page 92. And we're going to do number 11, which is using the definition of continuity and the properties of limits, show the function is continuous at a given number a. So they're going to give us this function, which is f of x is equal to x plus 2x cubed to the 4th. And they're going to say that a is equal to -1. And then let's also do 13, which is going to be, we have p of b is equal to 2 times root 3b squared plus 1. Always got to get these roots in here, where a is equal to 1. So for 11, we want to use the definition of continuity and the limits to show that it is continuous at 1. So what is the definition of continuity that we want to use? Like what is it that we're looking to show here? We're saying like we have one point that we're looking at. Yes. So there's 3 criteria, right? We have this general statement that it's continuous at a point if the limit at that point is equal to the function at that point. Exactly. So we need to say that f of a exists. We need to say that the limit exists, and we need to say that they're equal to each other. So this is kind of what we're looking at. Those are the 3 type of criteria, and it's defined. Yes, so I think you're kind of like answering the question there where you're saying this is defined at a is equal to 1, right? So this function exists. We can find out what a of equal to 1 is. F of 1 is equal to some number. And we can could find the number if we wanted to. I don't think we really need to. Actually, we do really need to, because we need to find out we need to equate it to the limit. So sorry. Whoops. Back into the algebra life. So f of 1 is going to be equal to 1 plus 2 times 1 cubed, which is 1 to the 4th. So this is 3 to the 4th. So that is 27 times 3, 81, right? Negative 1? Negative 1. Negative 1. Negative 1, not 1. Negative 1. So now it's negative 1 plus 2 times negative 1 to the 4th. So this is going to be 1 minus 2, so negative 3 to the 4th. Still going to turn out to be 81, because when we take it to the 4th, it's going to end up being positive. We don't like maintain, it'll be negative 3 times negative 3 times negative 3 times negative 3, which will end up being positive. It is 81, right? Yeah. So that's what f of a is equal to. And now we got to use f of, or we need to find the limit as x goes to negative 1 of x plus, or the quantity x plus 2x cubed to the 4th. And the way that we can do that is just by simply plugging in negative 1, because that's the kind of function that we have. And so this limit is going to be equal to negative 1, the quantity negative 1 minus 2 to the 4th, which is going to be equal to 81 again. So not only do we have the limit exists, we also have the function existing, and they are equal to one another. So it is continuous. Okay, so let's quick use that exact same like process for number 13. We can say that p of 1 is equal to 2 times 3 plus 1, which is equal to 2 times 2. And then we can say that the limit as v goes to 1 is equal to the same thing. So this is just like a very long-handed way of saying like this is equal to this is equal to this, and therefore it is a continuous function. Yeah, this is the long way of proving it. Let's try one more problem. Let's see if we can find one that's not necessarily continuous. Maybe 23. Oh, 17 through. Yeah, let's, do you want to do 23? Do you want to do, maybe 19? Let's try 23. So 23, we have this function where we have f of x is equal to x squared minus x minus 2 over x minus 2. And we're asked to quote unquote remove the discontinuity. Basically, we're trying to like turn this into a continuous function. So, sorry, I'm like trying to figure out exactly what they want from this problem. What do they want for this problem? Move the disk one. How would you define f of 2 in order to make f continuous at 2? How would we define f of 2? Okay, you have an idea, which is to say that this is x plus 1 times x minus 2. Yeah. What do they mean by defining f of 2? So this I agree with. I'm not sure what they mean by, because then we would just say that maybe they just want us to say that f of 2 is then equal to 2 plus 1 is equal to 3. Oh, yeah, that makes sense. So now, like, yeah, okay, I get what they're trying to do here then. Do you kind of see, I guess, what happened in this problem? And the important part, I think, was this part, in making it into a problem that we can, like, see as continuous. And so, yeah, so if f of 2 is equal to 3, then it is continuous, I guess, at 2. So, why don't we try one of the other discontinuous problems? Let's not do number 19. Let's do number 21 because we've got a trig function in there, and everyone hates those. So here we have f of x is equal to cos x 0 and 1 minus x squared. So this is if x is less than 0, if x equals 0, and if x is greater than 0. And we're trying to explain why the function is discontinuous at the given number, which is a. Here a is equal to 0. And we want to sketch a graph of the function. So why is this discontinuous at a? Let's do this in several parts. First, let's find the limit as x goes to 0 from the left, which means that we're going to be finding cos x. Let's do this from the right, which means we're looking at 1 minus x squared. So what are these limits? The limit of x approaching 0 from the left of cosine of x. Cos of 0 is equal to 1. And what about x approaching 0 from the right of 1 minus x squared? What is this limit? 1. So we have the limit as x goes to 0, generally speaking, of the function f of x is equal to 1. But we also know that f of a, which is essentially f of 0, is equal to 0. So while this limit exists, back to like our definition of continuity, this exists. They do not equal to each other. So it is not continuous at that point. I don't think we really need to sketch a graph of the function, but what could I do to make, what could I change here to make it continuous? If I just was to go into the problem and I want to turn it into a continuous function, I could just say that if x is equal to 0, then it's equal to 1 instead of 0. Exactly. You guys got this. Okie doke. That's pretty much what we covered this week. Do you guys have any other questions about this material? Not so far? Well, that's good. You guys are sitting in a good spot then. Yep. This is a really interesting class. I learned so much from my calc class, and it's a lot to process, I think, at times, but it's really, really interesting. So thank you guys for coming. If you have any questions during the week, feel free to email me, and we can for sure talk about them in the session, or if you're not in the session, email me anyway, and I'll talk about them and post the video so you can see the problems. And a lot of times people will send like WebAssign questions because WebAssign can do some wonky stuff sometimes, but we can always walk through it. So yeah, that's all I've got. And if you guys don't have any more questions, I guess we can sign off. Thank you so much. You guys have a great day.